Hey everyone, and welcome. We're about to tackle every single important graph you'll need for your IGCSE physics exam. And you know what? We're going to make it super simple and clear. So, do physics graphs have you feeling a bit overwhelmed? Yeah, I get it. Looking at all those lines and axes can seem really intimidating at first. But trust me on this one, they're way simpler than they look. Our whole mission here, to make them simple. In just the next few minutes, we are going to cover every key graph you need to know. We'll break them all down so they're easy to get, and more importantly, easy to remember. Ready? Let's do this. Okay, here's our game plan. We'll kick things off with motion, then hit forces, pressure, and momentum. After that, we'll look at thermal physics and waves, then light and optics, and we'll wrap it all up with electricity and magnetism. It's a nice, logical flow that's going to cover everything you need. All right, first up, mastering motion graphs. Let's really get into what these lines actually mean. Seriously, think of these graphs as little stories that show us exactly how something is moving. Okay, this is a big one. This clears up something that trips up so many students. On the left, you've got a distance time graph. See that flat horizontal line? That means you're not moving at all. You're stationary. But now look over at the speed time graph on the right. That same flat line means you're moving at a constant speed. So a straight sloped line means constant speed in the first graph, but constant acceleration in the second. It all comes down to what's on that vertical axis. Getting this is absolutely key. So what if they ask you to find the distance from a speed time graph? It's easier than you think. The big secret is that the distance is just the area under the graph. All you have to do is break that area up into simple shapes you know, like rectangles and triangles. Calculate the area of each one, add them all together, and boom, that's your total distance traveled. It works every time. All right, let's talk about terminal velocity. Picture someone jumping out of a plane. As they fall, they get faster and faster, right? Well, as their speed increases, the air resistance pushing up against them also increases. Eventually, there's a point where that upward push of air resistance perfectly balances the downward pull of their weight. At that exact moment, the forces are balanced, there's zero acceleration, and they fall at a constant, maximum speed. And that, my friends, is terminal velocity. Okay, moving on. Section 2, forces, pressure, and momentum. Let's see how we can visualize these really important principles. This one's all about balance. Think of a seesaw. A moment is just a fancy word for a turning force. For that seesaw to stay perfectly level and not tip over, the total clockwise moment has to be exactly equal to the total anti-clockwise moment. They have to cancel each other out completely. Simple as that. Clockwise equals anti-clockwise. So what is momentum? Well, you can think of it as mass in motion. The formula is pretty straightforward. Just mass times velocity. But here's the really important part you can't forget. Velocity has a direction, which means momentum does too. So if a car moving to the right has positive momentum, a car moving to the left would have negative momentum. This is super important when you're dealing with things like collisions. Ever notice how your ears pop when you dive deep in a pool? That's because pressure in liquids increases with depth. The formula is right there. P equals rho times G times H. That's density, gravity, and depth. But here's a pro tip. Don't forget about the air. The atmosphere is also pushing down on the surface of the liquid. So if you need the total pressure, you've got to add that atmospheric pressure on top. All right, let's switch gears to thermal physics and waves. This is where we get to see how energy changes things and how waves move. This is a great comparison. On the left, we've got a heating curve, and on the right, a cooling curve. Now, look closely at those flat parts, the plateaus. That's where the magic happens. When you're heating something, say ice, the temperature stays flat while it melts because all the energy is going into changing the state from solid to liquid. The same thing happens when it boils. The cooling curve is just the exact opposite process, condensing and freezing. Okay, diffraction. It sounds complicated, but it's really just waves spreading out. Imagine waves at the beach passing through a narrow gap in some rocks. They don't just continue in a straight line, right? They spread out in curves on the other side. And here's the key fact to remember for your exam. You get the most diffraction, the most spreading, when the size of that gap is about the same as the wavelength of the wave itself. Okay, on to light and optics. You're going to see how a few simple lines in a ray diagram can explain pretty much everything about how light works. This is a rule you absolutely have to know, the law of reflection. It's super simple. The angle the light comes in at, which we call the angle of incidence, is always equal to the angle it reflects at. That's it. I equals R. This one little rule is the reason why the image you see in a flat mirror is upright, looks like it's behind the mirror, and is laterally inverted, flipped from left to right. Now, converging lenses are pretty cool because they can make two totally different kinds of images. It all just depends on where the object is. If you put the object super close to the lens, you get a magnified, upright, virtual image. Think of a magnifying glass. But if you move the object further away, beyond the focal point, you suddenly get a real, inverted, that's upside down, image. And that's exactly the principle behind a projector. You know when you see a rainbow coming through a prism? That's dispersion. See, white light isn't actually white. It's a mix of all the colors. When it hits the prism, each color bends a little differently. Red light bends the least, and violet light bends the most. This is what separates the light out into that beautiful spectrum of colors. Just remember Roy G. Biv, and you've got the order down. All right, we're on the home stretch. Our last section, electricity and magnetism. Let's look at the key graphs you've got to know here. This table is an awesome summary of IV graphs. These graphs just show you what happens to the current as you change the voltage. For a standard resistor, it's a perfect straight line. The resistance is constant. But for something like a filament lamp, you get this S-curve, because as it gets hotter, its resistance actually increases. And then there's the diode, which is basically a one-way street for current. Almost no current flows in one direction, then suddenly it shoots up in the other. Transformers are all about changing voltage, and the secret is in the coils. It's really straightforward. A step-up transformer increases the voltage, and it does that by having more turns on the secondary coil than the primary one. And a step-down transformer, you guessed it, it decreases the voltage by having fewer turns on the secondary coil. More turns, more volts. Fewer turns, fewer volts. Okay, so let's boil this all down. What are your key takeaways? First, the gradient or the slope of a graph is always telling you a story about a rate of change, like speed or acceleration. Second, the area under a graph isn't just empty space. It has a real physical meaning, like distance. Third, when you see a flat plateau on a graph, it's a huge clue that there's a change of state happening. And finally, remember that ray diagrams and IV graphs just follow simple, predictable rules. If you can get a handle on these core ideas, you'll be able to read any graph they throw at you. And that's a wrap on IGCSE physics graphs. If you feel like you could use some more personalized help to really nail these concepts, check out Fundoo Tutor. It's a personalized learning platform designed to help students like you succeed in Cambridge, IB, and other international curriculums, offering expert mentorship and great resources. Thanks so much for joining me today, and best of luck with your studies.